Hello, we're going to be using the tabular integration method using exponentials. Let's say we had some integer a, that could be any integer, and that is raised to the x power. If we want the derivative with respect to x of a raised to x, then that would just be a raised to x times the natural log of a. And then if we want the integration, a raised to x dx, that would just be the a raised to x divided by the natural log of a. Let's say we have the following integral. The integral of 8 over e raised to x dx, which for this purpose of using the tabular method, we're just going to rearrange as 8 raised to x times e raised to the negative x dx. Well, for tabular integration, we need to have one function that we are comfortable taking the derivative of, and we have one function we're comfortable taking the integral of. Usually with the tabular method, we want the function we differentiate being differentiable all the way down to 0. So x squared to 2x to 2 to 0. We don't have that situation here, but that doesn't matter. We can still use tabular integration. Let's say the function we use as the one we'll take successive derivatives of, we'll take e to the negative x, and then the first derivative will have negative e to the negative x. And then the other function we have 8 raised to x, which if we integrate that one time, that would be 8 raised to x divided by the natural log of 8. With tabular method, what we care about is usually diagonals, but in this case, we're going to use our last term as a horizontal, which means that that last term is going to be a partial integral. So at this point, what we have is the diagonal e to the negative x times positive 1, because that will be our first term in our equation, multiplied by 8x over the natural log of 8. Then our second term, or our horizontal in this case, is going to be negative e to the negative x times 8x over natural log of 8 times negative 1. That negative 1 is because that is going to be part of our second term in our right side equation. So right now we have the natural log of 8 raised to x e raised to negative x dx equaling 8 raised to x e raised to negative x over the natural log of 8 plus the partial integral of 8 raised to x e raised to negative x all over the natural log of 8. If we keep going, what we see is if we pull out that constant 1 over the natural log of 8 on the right side, we have an integral with an integrand that's the same as what we were starting with. So let's take those two integrals and move them to the same side, to the left side of our equation, where essentially if we have our original integral minus our original integral times 1 over the natural log of 8, we can pull out like terms and do the following. We have the quantity of 1 minus 1 over the natural log of 8 times our starting integral equals 8 raised to x e raised to negative x over the natural log of 8. Divide by that constant on the left side, and what we're left with is our integral of interest equaling 8 raised to x e raised to negative x, which could be rewritten as 8 over e all raised to x, divided by the quantity 1 minus 1 over the natural log of 8 times the natural log of 8, which if we multiply that natural log of 8 into the parentheses, our denominator now becomes the natural log of 8 minus 1. So the integral of the quantity 8 over e raised to x dx is just the quantity 8 over e raised to x over the natural log of 8 minus 1 plus c. If we wanted to, we can go further using the properties of logs. That natural log of 8, that's really 2 raised to the third power, which if all of that is in our argument, we can pull out that exponent 3 as a multiplying coefficient in front of the natural log. So the denominator, natural log of 8 minus 1, is the natural log of 2 cubed minus 1, or 3 times the natural log of 2 minus 1, 3, 2, 1. So another way to write the integral of the quantity 8 over e raised to x dx is just the quantity of 8 over e raised to x all over 3 times the natural log of 2 minus 1, and then plus our variable constant, our random constant c, our integratable constant c. Although, just to prove a point, in this particular situation, we could actually swap which functions we're actually differentiating and integrating for our tabular integration. For example, let's say the integral we take the derivative of would be 8 raised to x, which its first derivative would be 8 raised to x times the natural log of 8. And if we integrate e to negative x, well, that still just becomes negative e to negative x. Taking all of our diagonals that we have possible, that's going to set our original integral equal to the quantity of 8x multiplied by positive 1, because this is our first term, multiplied by negative e to negative x. And since our next term is not going to be a diagonal, it's going to be a horizontal, we're going to have the integral of 8 raised to x times the natural log of 8 multiplied by negative 1, because that is our second term, multiplied by negative e to negative x. The negatives just cancel, and we're left with what's on the bottom. Doing a similar story, pulling out that constant, we're once again left with that constant natural log of 8 on the right side. We're left with our integrand of interest on both sides of the equation. Move them over so that they're on the same side. We're left with the quantity 1 minus natural log of 8 times our integral of interest equals negative 8 raised to x e raised to negative x. Dividing out that constant on the left side, that just becomes the negative times the quantity of 8 over e raised to x over 1 minus the natural log of 8, which if we plug in that negative 1 into all the terms in the denominator, that just becomes natural log of 8 minus 1. What we're going to see here is that no matter what we have, as long as we're taking the integral of some integer divided by e, whether that integer is 1, 3, 5, whatever, what we're going to end up having is, and I should say these are, a is some value greater than 0. What's going to happen is we're going to have our integral always equal to the quantity of a over e raised to x divided by the natural log of our numerator a minus 1. But that shouldn't be a surprise. If we didn't use tabular method, we could have just used our basic properties of exponentials, which is a over e. That's an integer divided by an integer. That's still overall one integer. So if we treat a over e as one integer, then its integral of that integer raised to x will be that integer raised to x divided by the natural log of that integer, or a over e all raised to x divided by the natural log of a over e. Because of the properties of logarithms, the natural log of a divided by e can be broken up into the second line, where in the denominator we have the natural log of a minus the natural log of e. If you're dividing terms inside of a log, that's just like taking the log of the numerator minus the log of the denominator. And the natural log of e, since natural log is just log base e, natural log of the argument e just becomes 1. And that's why any positive a integer, such that you have the integral of the quantity a over e raised to x dx, that's just going to be the quantity a over e raised to x over the natural log of a minus 1, no matter what. And that's just using the basic properties of the integral of an exponential of some constant raised to x. So we didn't actually need to use the tabular method. But let's just say hypothetically we want to do the reciprocal, the natural log of e over a raised to x dx. Well, let's not use tabular method. Let's just quickly use our basic property of some integer raised to x, taking the integral of that. That's going to be that ratio again raised to x divided by the natural log of that ratio or that integer. In this case, e divided by a. Using log properties, that denominator can just be broken up into the natural log of e minus the natural log of a. Therefore, we know that the denominator is just going to be 1 minus the natural log of a. So the integral of e divided by some positive integer, all raised to x dx, is going to be the quantity e over a raised to x divided by 1 minus the natural log of a, whatever that bottom denominator is. So hypothetically, if we were given the integer, what's the integral of the quantity e divided by 9 raised to x dx? Well, that's just going to be the quantity of e divided by 9 raised to x, all divided by 1 minus the natural log of 9. And 9 is really just 3 squared, so the natural log of 3 squared can just be rearranged as 2 times the natural log of 3. And there we go. This video was just meant to be another way of looking at tabular integration, although in this particular case, we should really just use the normal properties of some constant raised to x and then taking the integral of that. In any case, likes and subscribes are not necessary, but they are appreciated, and this small channel is growing, and let's see how far we can take it. Appreciate the active viewing, and see you all in the next video. Peace.